The first step I took in defining a complete generator was to complete this dconv function. So here's my complete function, and I'm approaching this in the same way that I did the conv helper function. Basically creating a short list of layers using PyTorch's sequential wrapper to return these as a complete module. Okay, so I start with an empty list of layers, and then I'm defining a transpose convolutional layer using the passed in parameters. So some input and output channels, and I again plan to use a kernel size of 4, a stride of 2, and a padding of 1 to effectively upsample any input by a factor of 2 in the x and y dimensions. Then I append this transpose convolutional layer to my list of layers. And here I address the batch norm case. If the batch norm parameter is true, which is the default, then I'm creating a batch norm layer which will be applied to the outputs of my transpose convolutional layer. If the batch norm parameter is false, I'm not going to add anything more to our list of layers. Finally, I'm using the sequential wrapper to group my layers together and return them as a module that I can use in my generator class definition below. Next, I'll move on to defining the generator class. So I know that this generator will see a latent vector z as input. Then the first step will be to put this through a fully connected layer that gives us enough outputs to reshape into a deep and small layer. So in this case, I want to actually create a 4x4 by 128 layer from these linear outputs. And I'm choosing 128 just because I want to shrink this in half with 2 more layers to 64, then 32 eventually. So with this goal in mind, I'll want the linear layer to produce 4x4 by 128 outputs. Okay, now let's look at this class. I have my first fully connected layer. This takes in our latent vector z inputs and produces a desired number of outputs. This number was just defined by me with the goal of reshaping these into a 4x4 by 128 layer. So I have 4x4 and then convdim, which is 32, by 4, which is 128 here. Then I'm defining 3 transpose convolutional layers. I know I need 3 because I need to get from a size of 4x4 to my desired output image size of 32 by 32. So let's imagine what happens to our input as it moves through these layers. It starts as a 4x4 shape, then after the first layer it will become 8x8, then 16x16, and finally 32 by 32. You'll also notice that as I use my helper function, I'm going from deep layers and decreasing the depth as I create more and more transpose convolutional layers. So I'm going from a depth of convdim times 4 to convdim times 2 to finally convdim and finally 3. I'm using a kernel size of 4 for each of these, and allowing a batch norm layer to be applied to all but the last transpose convolutional layer. For my final layer, I know I'll have my desired spatial size of 32 by 32, and I also want my desired depth, which is going to be an output of 3 for an RGB image. So all these layers together complete my init function, and I can move on to the forward function. This should look pretty familiar with a couple of special and important steps. First, I'm passing my input x, which will actually be a vector z, through my first linear layer. This is going to produce a desired number of outputs that I'm then reshaping into the shape I want. So let's look at each of these dimensions. This -1 is going to be a placeholder for a batch size. Then I have some depth that's defined by my convolutional dimension. In this case, this will be the value 128. Finally, I have my width and height, which are just going to be 4x4. Then I can proceed with passing this reshaped output to my transpose convolutional layers. I'm passing it in sequence to my first and second transpose convolutional layers and applying a normal ReLU activation function. Finally, I'm passing this output to my third transpose convolutional layer and applying a tanh activation on this last output. So this returned output should be a generated image that's 32 by 32 by 3 in shape and with pixel values in a range from -1 to 1. The next steps will be to instantiate a discriminator and generator and set up our optimization strategy for training these networks.